Okay, so good morning. So some of you, I'm told, went through the notes that I gave to you yesterday as both a homework and complement to what I'll be doing in the class. There are some calculations which I don't have to do, which I don't have time to do in the class. And there are complements on the propagators, which are a summary of things you must get some familiarity with in order to fully understand the details of what I'm talking about. Now, it was pointed out to me that the note starts at equation 2 point something, suggesting that these are part of a more complete set of notes, which indeed almost exist, but and I was planning to have them ready before coming here, but life is full of surprises and I didn't have a chance to finish them. So for those of you who are interested, you may contact me in a couple of months, maybe there will be more notes. In the meantime, what I can do is provide to you references, and I will give you a list of references. These are references to my own work with various collaborators. Andrea Beraudo is one of them. Actually, the first one, the first paper I'm going to mention was written with him and Claudia Ratti. So this is references, again, to my own work. Doesn't mean that this is the only thing you should look at, but you will find in most of this paper, particularly in the introduction section, complete set of references. And besides, much of the notation which I am using in the class will be, you will find the same modulo minor changes in this paper. So this is the first paper. It's one of the very first paper dealing with real and imaginary potential. This is almost the title of the paper. The very first paper is due to Mikko Laine and his collaborator. And Mikko was visiting us in Trento when I was there, together with Andrea, in fact. And we got interested, and this is how the whole thing started. I had interest in this problem for many, many years, but this was really a turning point where new theoretical ideas were injected, and found that interesting. The other paper which I want to refer to is also a paper with Andrea and other people. It concerns the calculation of a path integral of the kind that I've been discussing here. Even though these are ordinary Feynman path integrals, this is usual quantum mechanics. I mean, not quite usual, but ordinary quantum mechanics. The path integral, in particular with the influence functional, which is a non-local correlator between different points on the same path, it turned out to be difficult to evaluate analytically. And we tried to do that numerically, but we have to go to do that numerically. You have, for reasons that Gert has explained to you extensively, I believe, we have to go to Euclidean space, namely imaginary time. And then if you want to reconstruct the useful information, you have to return back to Minkowski. And that involves an ill-defined problem. And people have been using various techniques based on statistical analysis. A famous one is the maximum entropy method. But somehow we gave up at that point because these methods are not really, for the kind of problem we were looking at, were not really trustable. Then I decided that we should really turn to real time, and this is part of the techniques that I've been trying to teach you during these classes. And the important paper is this one here, where we did for QED, we carried through the program which I have started to outline for you in the case of QED, namely abelian interaction. And there we could go all the way to the complete description of the system. I'm using techniques that I will continue to explain to you today. You could describe the effect of collision, the effect of screening, the effect of bound state dissociation, bound state recombination, make connection with rate equation. All this could be done within the abelian context rather, well, I should not say straightforwardly, but could be done. And then it turned out that, so this is QED problem, abelian problem. It turned out that the extension of those techniques to QCD is not at all straightforward, for reasons that I will explain in detail in the last lecture, not tomorrow, but on Friday morning. And this involves two more recent papers written together with Miguel Escobedo, which exploit fully the techniques that I am describing. So these are difficult papers, even for the authors to read them after 2 years. It's hard. So you should not start by this, but hopefully with the lectures that you're attending now, you should be able, for those of you who are interested to know more, to read these papers. I should also mention another, which is more of a review on all connection which have been hinted at on the high gluon density. This is a review that I wrote a few years ago. And again, this is, you will find there more discussion of some of the connections that I mentioned between McLaren-Venugopalan model, momentum broadening, color glass condensate, and all this. This is partly discussed in this review paper, where again you will find much more connection with the literature. So, among the texts that I distributed yesterday, there is one which is an explicit calculation of the QED influence functional. So the calculation is done in great detail. So that should be, that's to complete what I've been doing in lecture. And there is one also on the density matrix and derivation of equation for the density matrix, which are not very difficult. But I will not have time to do that explicitly in class because it takes time just to write the lengthy equation. But I invite you to go through that, try to at least understand what's going on. I will say a few words about it in the second part of the lecture today. But that will be useful as a basis for the last lecture to understand why QCD is more difficult than the QED. So I invite you to look at that and eventually with the help of Andrea in the tutorial classes. Okay, so this being said, let me start by asking you whether you have questions about the last lectures. No? Okay. Anyway, I'm going to summarize briefly what we did last time. So what we did last time, we considered the correlator for two particles, which I refer to as a quark and an anti-quark, two heavy particles. And this correlator is a function, of course, of the coordinate of the particle, but also function of time. And if you wish, it's convenient to draw a little diagram where time starts at t0 equal to 0 up to t, and the two particles propagate between these two times. And I am interested in this correlator, and we wrote for that correlator a path integral. T is integral over all paths, where x here denotes the coordinate of the quark and the anti-quark. So there are paths which are composed of two branches, if you wish, or two paths. Exponential I S0 of x, and exponential I, this influence function of the path. And the paths go from some initial location to a final location. Okay? And I wrote the expression of this functional explicitly. It's a half the integral from ti to tf integral over 2 times tx and ty, and an integral over coordinate space x and y times the rho of x tx, a correlator delta of tx minus ty, x minus y times rho of y. Okay? And I remind you that rho is given by rho of x, and rho of x, let's say, is given by simply g, the charge or coupling constant, multiplied by the local density, x minus the operator, the position operator, minus. The minus is a charge for the anti-quark, minus g, x minus r bar at, and r bar at is the position operator for the anti-quark. Okay? And when you write this explicitly, you see the delta function will fix the coordinate in the propagator to be the location of the quark or the anti-quark along the path that is considered. And I gave you an example last time, and I got a little bit confused, so that's why I spend a minute coming back to this expression here. It's minus g squared times the integral from ti to tf dtx dty times the propagator tx minus ty r of tx minus r of ty minus r bar of ty. Okay? And that is correct, but that concerns only one part of the influence functional. There are 3 parts. There is one in which the quark is interacting with itself, the part where the heavy quark is interacting with itself, and this is where the other component, you remember yesterday I had a function delta of tx minus ty and 0 in the large mass limit. This is where the other pieces were coming from. I just got confused for a moment about that. So let's remind you what happened in the limit where m goes to infinity. We will soon relax this approximation, but then it is simple to see what's going on. If the mass goes to infinity, the location of the quark or the antiquark will not change. So this part of the contribution here for the full functional phi of x will remain unchanged. So there will be minus g squared, the integral dtx dty. There will be time dependence, but then r minus r is fixed. And then the other 2 components, which I did not write last time, namely the component where the quark interact with itself or the antiquark with itself, will give me a factor delta tx minus ty and 0. Okay? The factor 2 coming from here, you see, some of you made the observation that there are 4 terms. Indeed, there are 2 terms per density, so 2 times 2 is 4. With one half of these 2 terms kills this factor 2. That's the g squared that remains, and the other 2 terms are what I have displayed here. Okay, so at that point, I made a Fourier transform. Yeah, you have questions? No? Ah, sorry. Yeah, you should watch out because it's very hard to. I mean, writing with a chalk goes much slower than my brain thinks, and sometimes I make mistakes. So be careful. Don't hesitate to interrupt. I mean, if I write nonsense, which can happen. Okay, so Fourier transform. So I wrote delta of tx minus ty is equal d omega over 2 pi exponential minus I omega tx minus ty times delta of omega. I'm not writing the other arguments, but the spatial coordinates are in touch. And that is equal, that's a simple integral to do. I can now integrate, what did it say? No, I'm sorry. Yes, then I want to argue about the following thing, and I should perhaps do that a little bit more carefully. You see, we are interested in a situation where the response of the plasma occurs on time scales which are of the order of the inverse of the Debye mass. It's characterized by delta t, which is of the order of the inverse of the Debye mass, and the delta x, the typical size of the perturbation of the plasma. When you make a heavy quark, we put a heavy quark in the plasma, that will disturb the plasma on length scales which are of the order of the inverse of the Debye mass. Now, on that scale, the heavy quark doesn't move very much. You see, the velocity of the heavy quark is, if we are not too far from thermal equilibrium, is a thermal velocity. And the thermal velocity, as we argued in the first lecture, is the square root of T over m. Right? And that's assuming that m is much bigger than the temperature. This is much smaller than 1, much smaller than the speed of light. That means that during the time delta t, the distance, let's call that d, traveled by the heavy quark is of the order of the thermal velocity times md minus 1. Okay? And that is a small distance compared to md minus 1, which is the size of the perturbation induced by the heavy quark in the plasma. Okay? So the idea is that by the time the quark has moved a little, I mean, when the plasma reacts, the heavy quark doesn't really move. Okay? So that's the basic assumption, that during the time, so during the time delta t of that order of magnitude, the heavy quark moves a distance which is small compared to the size of the perturbation. Say differently, the frequencies that I'm going to probe in the plasma are very small compared to the Debye. And that's a basic assumption which underlines all what I'll be doing today and the next time. I mean, not quite all, but it will bring a major simplification. So under this condition, I'm going to do a very drastic approximation, namely set here omega equal to 0. Okay? In other words, what I'm saying is that the heavy quark on long time scale will be only sensitive to the static response of the plasma. Okay? Okay, so let's do that. So heavy quark sensitive only, well, I put only in quotation mark, we will improve on that later, to static response. And then I'm going to do something which is not, which will lead to a result which is not perhaps immediately intuitively obvious, but I'm going to rewrite delta of tx minus ty as I'm going to factor out delta of omega equal to 0, and then what remains is an integral d omega over 2 pi exponential minus I omega tx minus ty, and this is just 2 pi delta of Tx minus Ty times delta of omega. Okay? I used a different argument yesterday by calculating explicitly the integral with leading to cosine and taking the large time limit of the cosine. But this is equivalent way of reasoning. And this reasoning I will extend, later to calculate corrections. So you see what it says is that I am, yes, if I look at my correlator over there, this is T0 and T. So I have the quark, the anti-quark. This is R, this is R bar. And then I have different types of interaction. But what this statement here means is that these interactions are essentially instantaneous. Tx, T prime with T equal to T prime. Okay, I can have also interaction involving the heavy quark or the heavy anti-quark. These are simple tadpole, local in space and time. Okay? So this being done, I can return here. I had two integrations of a time. So I have taken care of one of them. So there remain one time integral. So phi of x will be equal to minus g squared times the integration of one of the time will give me a factor Tf minus Ti. And then I have the difference between T delta of omega r minus r bar minus delta omega equal to 0, sorry, delta of 0 and 0. Okay? Well, this is taking care of the interaction between the quark and the anti-quark, and this is taking care of this tadpole insertions. Okay? Is that clear now to everybody? Okay. Okay, so you see, this assumption that the plasma response is nearly always static has a profound implication, because it's remember, this kind of correlation here, this delta, is taking care of the collision with the medium. Okay, perhaps I should remind you that this part of the correlator would lead to I will have to spend a minute more on this. But this will lead to the potential, which contains a real part, this combination here, plus an imaginary part. And remember, we discussed yesterday that the imaginary part is actually reflecting the presence of collision in the system. What we're saying here is that these collisions are essentially instantaneous, and that brings a tremendous simplification, because what is hard with collision is to describe situation where the second collision starts while the first one is not completely finished. Here, since the collision is instantaneous, the second one will start infinitely later the first one. And that's a simplification which allows, in particular, to lead to factorization and that kind of thing, or exponentiation of some of the process. Okay, so perhaps I should say a little bit more. So this is a parenthesis, a technical parenthesis on the propagators. And this is where the notes, which are really what I call the survival kits, can be useful for those of you who want to really play with the details. Let me digress on propagator, because I want to make a point I want to make some point about that. So I can write, this is a general propagator now. I call it delta, but it goes for all kind of propagator. I can write it in terms of the so-called spectral function, dq0 over 2 pi, from minus infinity to plus infinity, rho of q0 divided by q0 minus omega, this omega here, minus I eta plus I rho of Q0 and Q times n of omega. And this n of omega is just the Bose-Einstein distribution function. N of omega is 1 over exponential omega over t, where t is the temperature, minus 1. That's true for the time-ordered or the Feynman propagator or usual perturbation theory. And that part of the propagator here is what is called the retarded propagator. When you Fourier transform, the presence of this I eta here tells you how to close the contour at plus infinity, and that generates a theta function in time. And that's a characteristic of the retarded propagator. So now, the point I want to make is the following. I mean, when you do imaginary time calculation, this omega minus I eta becomes a Matsubara frequency, I times omega n, when omega n is 2 pi n over temperature. So this, I mean, once you know the spectral function, by the way, you know everything you need to know about any propagator, retarded, advanced, ordered. It's just a matter of continuing in the complex place in the right way. I don't spend too much time on this, but the point I want to make is that this part of the propagator is analytically continued to the retarded propagator, I mean the retarded and all the propagators you know of. But if you want to do an imaginary time calculation, you can have access to this, but you will miss this contribution here. It's very important warning that when we calculate the free energy, for instance, as I did yesterday, it's an information which is contained in the correlator G, which is written over there, by changing T into minus I beta. This is fine. You get the free energy. But if you want to calculate this kind of information I'm talking about, you really need this piece here. You see there is an I, so that contributes to the imaginary part. There is a statistical factor which signals that this contribution to the propagator is actually dealing with fluctuation, in particular with thermal fluctuation, and that's not something which is contained in the imaginary time propagator. So if you want to know more about that, you can look at the notes. I mean, this is just a collection of formula, but in principle, everything can be deduced straightforwardly. And this is a warning I want to make. There are subtleties that we have to deal with, but there is also physics. I mean, if you spend enough time, there is physics involved in these various contributions. In particular, you see, we are interested, let me open a little window here. We are interested in the limit where omega equal to 0. This limit is rather straightforward because for omega equal to 0, in fact, the spectral density for most systems is an odd function of Q0. So rho of Q0 is minus rho of minus Q0. In particular, rho at Q0 equal to 0 is 0. So when we set omega equal to 0 here, because rho vanishes when Q0 is 0, there is no singularity, so you get a simple integral coming from the retarded propagator, dq0 over 2 pi, rho of Q0, let me drop the Q over Q0. So that first part is correct. And then you get I times rho. Let me write this. I'm interested in the limit where omega equal to 0. When omega equal to 0, this is singular because this is 1 plus omega over t minus 1. So this is t over omega. So this will be t. So let me write it as the limit when omega goes to 0 of t over omega times rho of omega. Okay? And this is a beast which contains the information about real part, I mean imaginary part. Okay, so this is a technical remark, just to invite you to play with those propagators if you are really interested in the details of what's going on. And then I will continue now to improve on the frequency approximation, on the small frequency approximation. You have questions here? No? Yes? I'm sorry, yes, this is... Well, you are asking about this formula here? This is I, the usual I, times the, I squared is -1, times the limit when omega goes to 0. You see, it's 1 over omega times something. So rho of omega equal to 0 is 0, right? But I don't know what rho of 0, what this limit will be. It turns out that rho of omega vanishes linearly with omega in most systems that we are dealing with. Okay, so it's just a way to write rho of omega over omega in the limit where omega equal to 0. That's all I'm saying. Okay, I cannot say better than that. Okay, you have other question? Yes? The imaginary part is calculated. We want delta for omega equal to 0 here. Okay? So if I set omega equal to 0, omega disappears.
Yeah, I'm talking on the second term. Is
I rho
of omega?
Oh, of course. I'm sorry. The what? Just a moment. No. You have a point. You have a point. No. This is omega. This is omega, of course. It doesn't make sense. Q0 is integration variable. Yes, thank you. This remains true, independently of the notation. But this is rho of omega. Yes, thank you. Yeah. In fact, you see, there is another contribution of this type here hidden. It's a vacuum fluctuation. If you replace this I omega by principal part plus I pi delta, you will find a delta of Q0 minus omega, which fixes omega, and you will find a 1 with a factor of half, because it's pi delta, there is factor of half. So you will replace this factor by 1/2 of 1 plus 2n omega. And that's a typical factor you get for fluctuations. The one reflecting vacuum fluctuation and the n, the thermal fluctuation. So more on frequency, on the low frequency approximation. Yes, it's still here. So I'm going to improve on what I've done here. You see, I've been arguing that what counts are frequencies which are small compared to the Debye mass. And then I have argued that the simplest approximation consists in setting omega equal to 0. But I can do better. In particular, I can expand omega as delta of omega equal to 0 plus omega d by d omega delta of omega plus calculated at omega equal to 0 plus etc. Right? So if I inject this expansion in this relation here, I will get the following expression for delta of Tx minus Ty. And that is delta function, that's a term which we have kept, times delta of omega equal to 0, plus I d by dt x, delta tx minus ty times delta prime of omega equal to 0. And this delta prime for omega equal to 0 is just this, right? And then I can repeat the calculation, okay, by including these terms. Now it turns out that these terms don't play much of a role for the correlator, but they are important for the probability. So now I return to the probability P of xf/tf, xi/ti. Remember, when we deal with probability, we are asking a different question than when we did with the correlator. Here we are really asking what the probability is to find the quark at location tf at time tf, given that they were at location xi at time ti. Okay, it's not an amplitude, it's a probability. And then for this, so I insist, probability, and probability are closer to the density matrix than to functional integrals. That's why I switch from time to time, and I will do so later, to density matrices. But we can calculate for the probability, we can calculate the influence functional, and I would like to write it up explicitly for you, okay, in order to explain a number of issues. So the calculation is almost identical to the one we did for the correlator, but now we have to combine terms in a different fashion, and there are additional terms. And let me write just the part of the functional which concerns the quark and the anti-quark. So that will be minus g squared times integral ti to tf. Now there is a single time. So now I go, go on the contour. You see here I am dealing with time-ordered propagators because I'm just looking at propagators. Everything goes from t0 to t. Now, since I'm looking at probabilities, I have an amplitude and a complex conjugate amplitude, and I have to write things in a simple way, I have to use this contour integration. So this is what I do here. Perhaps I should draw a little diagram there. That could help. So this is, again, T0 and T, and the quark and the anti-quark. So let me see, in my notes here, I am calling the quark Q, so coordinate Q1. The quark downstairs will be Q2, and I have Q1 bar, Q2 bar. Remember, as I discussed earlier, we can either let the time run on the contour or split the coordinates, double the coordinates. This is what I'm choosing to do here. So I have two coordinates for the quark. The quark on the upper branch of the contour I call Q1. The quark on the lower branch of the contour I call Q2. Okay? And then I'm going to write the expression I get. So V of Q2, so the V is coming from the same manipulation. It's related to the imaginary part, to this kind of decomposition here. So I get V of Q2 minus Q2 bar minus V of Q1 minus Q1 bar minus I. So this is a big term inside the integration, minus IW of Q2 minus Q2 bar minus IW of Q1 minus Q1 bar plus IW of Q1 minus Q2 bar plus IW of Q2 minus Q1 bar, and it's not finished, plus 1 over 2t times Q bar two dots, the dot denotes a time derivative, d by dq2 bar w of q1 minus q2 bar. I hope I'm not making mistakes in copying all this. q1 bar, d by dq1 bar, w of q2 minus q1 bar. That's it. Okay, so what do these terms correspond to? In terms of diagrams which I've been drawing all along, you see, this is the real part of the potential that contains the quarks and the anti-quark in the lower part of the contour. So this is an interaction which I can draw by a diagram like this. And then I have a similar interaction upstairs for the quark number 1, right? And then the W, well, the W will contribute, so this contributes to the real part of the potential. I mean, this is the effect of the interaction between quark and anti-quark. That part, that upper part is what is contained in the correlator. And there are terms which are also contained in the correlator, which involve the imaginary part, W. So I have also, I don't know how to write this, the W, I write zigzag like this. I have also one between these two beasts here. And then I have new terms. You see I have a term W of Q1 minus Q2 bar. So Q1 minus Q2 bar, you see I have an interaction. It's not very, yeah, I have an interaction between this anti-quark here and this quark here. So this is typically a quantum mechanical effect. I mean, this is really, you see, it's a connection, it's a correlation between emission of a gluon, if you wish, in the amplitude, and that gluon being reabsorbed in the complex conjugate amplitude. So that's not part of the correlator. It's something which contributes to the probability. And then I have another one which is the same thing, but between Q2 and Q1 bar. Okay? And the last term, which involves the time derivative, are obviously coming from this expansion here. And you will see a little bit later that this term actually, in spite of the fact that I have done an expansion which suggests that they should be smaller than the leading term, in fact, you will see that in the semi-classical approximations, they are of the same order of magnitude. And these are the terms which contribute to the dissipation and friction. Now, I can make another remark. You see that when in the infinite mass limit, it's always good to think, to look at what happened when the mass is very large, because things become much easier. In the infinite quark limit, the coordinates are frozen. So Q1 is equal to Q2 at all times. There is no, I mean, it's independent of time. This is the same for Q1 bar and Q2 bar. And you see that under this condition, these two terms cancel, because 1 and 2 are the same. And you can check that these four terms cancel among themselves. You might want to argue the same thing here, but it's a little bit more subtle. But in any case, the velocity is supposed to be small, so Q dot is going to 0 in the infinite mass limit. So you say the influence functional vanishes. And that was not quite the case for the propagator, right? We had this imaginary part which suggests that the propagator is damped over some period of time. But this damping factor here, you see, cancel. And why do they cancel? Because we are calculating a probability. And if the mass is very large, this probability in the limit when the mass goes to infinity should go simply to P of xf tf xi ti should go to a delta function of xf minus xi. That is to say, because the interactions are local, you cannot change the density of heavy quark, and the probability to find them at a location different from the initial one just vanishes. The quarks stay where they are. So you see, the calculation makes sense, at least in one limit, and the result is very different from that of the propagator. They look very close, but they are physically not the same thing. And that's important that you keep that in mind. Okay, so I would like to do one more thing before the break. And let me try to do that now. This is where I will rely on the part of the notes that I distributed, which concern the density matrix. So, I need that. So let me erase over there. So let me return now to the matrix. As I just told you, the density matrix is close to probabilities. Unless perhaps you have a question on what I just did, no? Is it clear? Yes?
Could you comment again on the physical interpretations of these terms that have the derivatives in Q? And what?
The time derivative terms?
Yes.
That will come, that will be easier to comment a little bit later when I've done the density matrix. Actually, what I'm going to do next hour is to show you how from this formalism the Fokker-Planck or Langevin equation emerge naturally. And this term will play a very important role. I mean, these terms are needed to satisfy so-called fluctuation dissipation theorem or things like this.
And they don't couple with the real part, right? Only with the imaginary part, without you?
Yes, it's a good point. Let's see. Can I answer that question? Well, no, it's not completely obvious. Well, physically, perhaps when you will see the equation for the density matrix, it will become more natural. But I don't have a very sharp and shortcut argument to help you understand. I mean, the way it appears is that if you have to go into the detail of this type of relation to see detail what the correlators are and how they behave in the appropriate limit. And there is no such term for the real part. In other words, there is no Q dot associated with V. It only occurs with W. In a way, it is physically natural because the potential is a local interaction which depends only on the position of the quark, not on their velocity, right? Whereas the effect of collision depends on the velocity because a collision, I mean, they may depend on the velocity. It's not obvious, but they may depend, and they do. Okay. Well, okay. Probably this will come a little bit sharper when I have done the density matrix. So now the question is, we started a little bit later, no? So I still have, but
If you need to complete a reason, it's better.
yeah, maybe I will do the density matrix. It's not very long. So back to density matrix. I hope you don't get lost with my how to say impressionistic action to present the problem. It's just that it's a difficult problem, as you may have guessed, and you get different insight depending on the way you look at it. And this is what I'm trying to convey. I mean, the technicalities are one thing, but getting insight is usually more useful. So let me rewrite the equation that I wrote many times already. This is the equation for the density matrix in the interaction representation. Okay? And this equation has the following solution. Di of t0 minus I, the integral from t0 times integration. Very hard. I'm not doing too much at the moment. But now I'm going to do something which looks innocent, but which is at the root of many of the approximation which you will find if you open a book on open quantum system. So what I'm going to do is to take this solution and re-inject it in the microphone is off. No, it's not. It is working. It is working. Okay, so let me do that. So di dt by dt is equal to, so I plug in here on the right-hand side, I plug the solution. So what do I get? I get minus I, h1i of t, d of t0, minus the integral from t dt prime, and then I get a double commutator. Okay? I'm just copied, just replace the solution, iterated if you wish once. So there is a first benefit, is that this term can be ignored. Because eventually, what I want to do is to trace the plasma degrees of freedom. And the reason I can ignore this is, remember that H1 is, as far as the plasma is concerned, is proportional to A0. So when I do the trace over the plasma degrees of freedom, I generate something which, in the interaction, will contain the average value of A0. And the average value of A0, by assumption, is 0. Okay? And then you see that this equation now doesn't contain terms linear in the perturbation. It's quadratic in the perturbation. If I would replace di of t prime here by di of t0, I would just have written a second-order perturbation theory. But you see, I can start doing approximation here, which are a priori not legitimate, but they will be legitimate because it's already a term of second order in perturbation. So all correction from that I'm going to implicitly assume here will be at least over the 2 or even higher. So let me give you one example of that. Yes, basis. I mentioned already that at the beginning we assume that the density matrix at time t0 is a product, is a tensor product of the quark density matrix times the bass density matrix. Factorized form. Now, if we have such a density matrix, it's straightforward to do the trace of the bass degree of freedom because there is a factorization. So we just integrate out the bass degree of freedom. That can be done usually in a straightforward fashion. So I'm going to assume that this relation holds at all time. In fact, more precisely, that di of t is approximately equal to diq of t times dB of T0. I put the same T0 because I'm assuming thermal equilibrium for the plasma, and I am assuming that the plasma doesn't move, doesn't change. The probabilities are given by Boltzmann factor at a given temperature. Nothing happened to the plasma. Now, because of this factorization, I can simplify this equation. And you see why is that not a stupid thing to do? Obviously, this is satisfied by the initial condition. And then if I inject this factorized form, the correction will be already of second order, the correction to the factorized form. So I'm making an error which is of order 4 in the perturbation. Of course, this is time-dependent perturbation theory, so one has to be careful about what's so-called secular terms, terms which are a priori small, but when you let time evolve, they can become big because the time which multiply all these factors, you see, this is an integration of a time. So it's not enough that h1 is small. I mean, the time h1 should remain relatively small, but nevertheless, this is a commonly used approximation. It is motivated by what I just said, and then that allows to write the equation in a simple form. And this is what I will be doing at the start of the next lecture. I think it's a good point to stop here. Okay, so if you have questions, it's also a good time to ask. Yes?
Why does only the anti-quark velocity?
Why?
Only the anti-quark's velocities appear.
Or it's just a matter of writing. You see, these are functions of Q1 minus Q2 bar. So the derivative with respect to Q bar 2 can be changed if you change the sign. I mean, it's nothing, no, there is nothing deep here. It's just a writing. Any other question? Okay, so we break until 25, okay? That's okay, Chairman? Even less. 5 minutes, okay, 5 minutes. If the, okay, so let me, I'm going to skip the details and write directly the equation that result from the approximation I just mentioned after performing the averaging over the plasma degrees of freedom. So I take the trace over B. That will give me on the left-hand side the density matrix, the reduced density matrix of the quark. And yes, and I do another thing. I should write what I do explicitly. So use this approximation. Take a trace which you can do because for two reasons. First of all, there is a factorization of the density matrix. And second, the interaction, remember the interaction H1 is of the form J dot A0, and this J is essentially the density N of X. N of X, right? So you see, part of the reason why the trace is easy to do is also due to the fact that the interaction is a product of an operator which depends only on the coordinate or the state of the heavy quark, and another operator which depends only on the thermal mass. Okay, so because of this factorization, it is straightforward to do the trace, and then the last step to get the equation is to return to Schrödinger picture. That is to say, undo the interaction representation. So I will be talking now about the density matrix in the usual Schrödinger picture, and that equation for the density matrix takes the following form: QD plus I HQ dq of t, so that part is easy. And then I'm going to write down the part which follow from the interaction. So f and x prime, v of x minus x prime. Then there is a commutator and x. So this I use to simplify the writing. I drop the parentheses and I write the coordinate just as an index, but these are continuous variable, and x prime dq of t prime. You will see some analogy with what is written on the right board, I hope. Plus 1/2 of the integral of x prime w of x minus x prime. And then there are three terms, which I can write as nx and x prime. So this curly bracket here denotes the anti-commutator, minus 2 times x dq of t prime and x prime. So that's the term coming from W. And then there is another term, which is I over 4 times the temperature. Again, integral x prime, W of x minus x prime times a commutator and x dot dq of t prime plus an x dq of t prime and x. I should also specify that in order to alleviate the notation, to save the writing, the time, these operators depend on time, of course. So x will be associated with time t and x prime with time t prime. But I'm going to simplify that in a second. So you can see that the structure is not too different from that of the functional, of the influence functional that I wrote on the right board. You see there is an interaction, the Vx minus x prime times the densities. This is a Coulomb interaction. And that part of the interaction between the two heavy quarks, that's a real part of the potential which is sitting here. And the other terms describe the same physics as in the functional, influence functional, which is here. You see there are terms which couple, you don't see that immediately perhaps, but there are terms in which you have a commutator with a density matrix that represent terms which are among quark and anti-quark, and there is a term where the density matrix is sandwiched in between, and that typically involve a cross term across the two branches of the Schwinger-Keldysh contour. So this is something which I'm not going to derive. It's already long to write on the board, but I am going to use this to proceed further. Incidentally, before I raise this board, I was asked to give you a little bit complement on the connection between the propagator delta and the potential and its imaginary part. I may be able to do that today, but if not, I will do that at the beginning of the next lecture. Okay? So, what do we do with this beautiful equation? Well, first of all, you see that the time, this is a closed equation now for the density matrix. We have eliminated completely the plasma degrees of freedom. What remains from the plasma is just the correlator, which have been expressed in terms of real part and imaginary part of the potential. And then we have to solve this equation. Now, part of the difficulty which we have to face is that this is an equation which is, you see, non-local in time. The density matrix at time t appears on the left, but there is a density matrix at time t prime on the right. I guess there must be yes, there must be some yes. So I'm going to do immediately. So this is what's called in the literature non-Markovian equation, because it depends on the history of the system at the time you look at it, not only at the local, you don't not only need the local information about the object, you need its history. And I'm going to make it local and Markovian. This again can be motivated by the same type of argument that I was discussing before, namely assume that everything is taken locally. Then this equation can be written. Now this is a Markovian equation in the form of a linear operator acting on dq of t. Okay? It's a complicated object, but you see it has the form d by dt of d is some operator, which may be complicated, acting on d. It's a linear operator. D appears in a linear fashion. And then I'm going to call, to give name to the various terms. So the first term here I'm going to call L1, this term L2, this term L3, and the term which contains the interaction I'm going to call L0. And what I want to do with you is to analyze the content, the physical content of this equation by looking at the one particle density matrix. So, single quark density matrix, and then I will indicate how to generalize to several quarks. So, we have to calculate those commutators here. Remind you that nx is n of x. It's a delta function, maybe with a g, which I may forget sometimes. Delta of x minus position operator, which means in other language that nx, the matrix elements of nx in the coordinate representation is just g times delta of x minus r, delta of x minus r prime. It's a diagonal operator in coordinate space. And yeah. Now, how to calculate n dot x? To calculate n dot x, I'm going to use the continuity equation. N dot x is a divergence of a current, so it's gradient x of j of x. And j of x is also a local operator, which involves derivative of the gradient of the wave function, if you wish. And that will, and let me give you the matrix element of j of x. That's 1 over 2im. It's the velocity, I mean the current is proportional to velocity, p over m, and p is a gradient. And just to make sure that you can do the calculation, let me give you an expression, x minus r plus delta of x minus r prime. Okay? You can write it in different ways, but this is a convenient way. With this information, you can calculate now, you can take a matrix element, you can take a matrix elements of this equation in the basis with r on the left, r prime on the right. Okay? And I'm going to calculate r, L1, r prime, L1d, sorry, L1d, r prime. These are linear operator, but they are not necessarily quite local. So this is what? This is minus I over 2 times an integral of x and x prime, v of x minus x prime, and then I have a matrix elements of R times nx and x prime d R prime. And this is 0. You see, it's fairly straightforward to see. This is a local operator, so x is equal to, I mean, if I look at the left, x is equal to r, x prime is equal to r. That goes away. I'm left with the matrix element R prime. But then in the commutator, if I take the commutator, well, maybe I could do it. So this is an x prime d R minus d and x prime R prime. So what I'm saying is that when this operator acts on the left, that fixes x equal x prime equal R, leaving a matrix element R d R prime, and when this is acting on the right, these two give me x equal x prime equal R prime, leaving a matrix element R d R prime. So this cancel. And this is expected. You don't expect the potential, the real part of the potential, to affect the affect the density matrix in neither the diagonal part or the non-diagonal part. We'll see that it is not the case for the other terms. Is that clear for everybody? So I'm doing a very simple what I'm trying to do, getting there is not very difficult. It takes time, just essentially writing the equation step by steps. But these equations, which look a little bit complicated, in fact, have a very simple physical content, which I'm trying to decipher for you. Okay, so it's somewhat similar to what we get for the probability up there. So now let's look at the second term. The second term is L2. And then I need to erase a part of the board. Oops. So L2. So let me calculate R L2 D R prime. So this is okay. So maybe I can do things a little bit quicker. You see, there will be a half, perhaps a half. Let me try to do it then. So there is L2 is. Perhaps I can make a short nevertheless. So if I take the first term, you see I will be in the same situation with w of x minus x prime. So that will give me on the left x equal to x prime. On the right, the same thing. So I will have a w of 0 in front. And then I will have the matrix elements R d R prime. This is dq always. Okay. Right? And there are two such terms, so that takes care of the factor half. Now the other term will be essentially the same, except that now I will have minus w, x is equal to r, x prime is equal to r prime, and the same r d r prime. So this is, and there is an explicit factor of 2 here, so that kills the factor half. So let me write this in the following way. Let me write this as minus gamma of r minus r prime, r d r prime, where gamma of r minus r prime is, I define it as the difference between w r prime minus w at 0. This gamma is essentially the function phi, which I discussed yesterday. You see, it vanishes for r equal to r prime. This is this dipole, small size dipole argument that I discussed yesterday. And what you see here is interesting for several reasons. You see that, where did I work? This is a linear equation I'm looking at. So if I look only at the term L2, what L2 will do is damp the non-diagonal matrix element. So there is damping of non-diagonal matrix element of the density matrix. And that damping corresponds to what one may call decoherence. It's a fact that the collision, you see, the non-diagonal matrix element, the fact that the density matrix is non-diagonal is a typical quantum mechanical effect. Density for classical particle is diagonal object. It means the particle is at given position. The fact that there are off-diagonal elements, and we'll come back to that in more specific terms in a few moments, it is a result of quantum interference between the constituent of the, or between the different waves which describe the heavy quark. And what this equation says here is that after some times, which is controlled by the inverse of gamma, the effect of collision, in fact, brings the density matrix to a diagonal form. In other words, makes the motion of the heavy quark more and more classical as time passes by. So this is the first statement that I want to make. And of course, that statement goes with what I was saying yesterday. You see that if R are close together, then the gamma vanishes. And that's just the statement that if you look at the density of particle, which is a diagonal part of this, then the collision don't do anything. They just don't change the density. Okay? So even though you have an imaginary potential, don't be confused. It's not describing the fact that the heavy quark disappears. And then now we have to deal with L3. Where is L3? Here is L3. So L3 is of the following form. Is there any question? No? Okay. So let me, well, you can repeat the same calculation for L3. Let me write down the result. You find that it is equal to 1/4 mt times the square gradient W of 0 minus gradient squared of W of R minus R prime times R dr prime. That's the result of one term, and there is another one for mt, which contains explicit R dependence in a different way, minus R prime, dotted. So this is, I'm not very good at writing the vectors, so this is gradient R minus gradient R prime. The whole thing acting on R dr prime. Now, it's not immediately obvious to see what this means, and to see that more explicitly, I'm going to do the next step. Okay. But I have written here explicitly for you the operator L for a single quark, and you see I obtain an equation for the density matrix in coordinate space, which you can think of solving. And this for one particle can be done, even for two presumably this can be done, but in order to make life easier, I will do a further approximation. You have questions, yes.
Maybe I just missed the point, but so this gamma function vanishes when R is small, right?
When gamma of R vanishes when R is small, yes.
So doesn't that mean that then there is no diagonal term, therefore there is only diagonal term, therefore the heavy quark is more classical in the very beginning of the movement?
No, because this is controlling the rate of change with time of the density matrix. So if you start with a density matrix which is non-diagonal, which you can always do, what this equation says is that it will become diagonal after a time of order 1 over gamma. Okay? here R and R prime are not the location of the quark. We're talking about more subtle information about the off-diagonal part of the density matrix. I can start with any density matrix. Of course, if you start with a density matrix which is diagonal, that's the density of the heavy quark, and that remains constant as a function of time, because gamma of 0 is 0. Okay? Does this answer your question? Or? Yeah. Yes. We'll see what we do with the non-diagonal part right now. Because that calls for a set of approximation which go under the name of semi-classical approximation. Yes. Yeah, yesterday when I discussed gamma, I was talking about two quarks, or one quark, one anti-quark. And I mentioned the fact that indeed the imaginary, I mean the effect of the collision was to produce an imaginary potential. And presumably I will come back to that tomorrow or Friday. But here we are seeing another effect of the collision, which is the effect of which is a genuine, how to say, it's erasing quantum mechanical effect. I mean, there's the effect of the collision that between, you see, there's a loss, when particles collide randomly, and this is essentially what is being done here, after one collision, you lose a little bit the memory of the phase of the wave function. And if you do that too many times, then after a while, the information of the phase of the wave function has disappeared. And this is what is causing this decoherence phenomenon. So it's a very general effect. So, semi-classical approximation. So the matrix elements of D, let me drop the sub-Q index. I mean, I'm talking now only on the reduced density matrix. So this I'm going to write as D of R prime. It's also a function of T. And I'm going to change coordinate, write this as D of capital R, little y, and T, where R is R plus R prime over 2, and the y is R minus R prime. So basically, you see, what I was telling you before is that when R becomes close to R prime, we are in a classical regime. So I want to expand with respect to R minus R prime and see how the equation transforms. And then you will recognize simple things. So let me do this transformation. At the moment, I'm just doing a change of coordinates. So I'll leave it to you to show that L0 becomes I over M, the gradient with respect to R times the gradient with respect to Y. As we have already seen, L1 is 0. L2 becomes minus gamma of Y. And L3 simplifies a bit. I'd like to write this on the same line. And L3 is equal to 1 over 4 times MT times, well, Laplacian W of 0 doesn't mean that I take the Laplacian of W of 0. It means it's again a shortcut for saying that I take the Laplacian of W of R and then evaluate it at R equal to 0. Okay, I mean it's not 0 in other words. Minus gradient squared W of Y, and then there is another term which I cannot write online, which is gradient of Y of W of Y dot gradient of Y. So you see the first two, I mean the L1 is 0, L2 is a local operator, And both L0 and L3 involve derivative operators. There is an important property of W which I have not used, that is the gradient of Y, which I've used in writing this, at Y equal to 0 is equal to 0. Don't think I can show that immediately. But this property is useful because you see if Y equal to 0, L2 is equal to 0, and this term is also equal to 0 because of that property. W, well, this cancels, and the gradient of W at Y equal to 0 vanishes. And that's needed in order to keep the density constant. So this property has to be true. It doesn't explain to you why it is true, but I don't have right now a better argument. So this is just an exact translation of what is written on the left in terms of these new coordinates. And now I can do the small y expansion, which is a semi-classical approximation. So I write that y of y, w of y is w of 0. And then, because of the properties that I was mentioning earlier, this is start with a quadratic form, h of 0 times y plus etc. And h is a so-called Hessian. It's a matrix of second-order derivatives, so it's a w of y over dyi dyj. Okay, I'm just doing a Taylor expansion. And then I can write explicitly the operator in the following way. So d by dt of d of r, y, and t is equal to, let me write the big operator here, I over m, gradient r, gradient y, so that's the kinetic energy, minus 1 over 2 y h of 0 dot y. So this means yi, hij, yj. And then the last term gives me minus 1 over 2 mt times h times, I'm sorry, y, h of 0, gradient with respect to y, and the whole thing is applied to d of r, y, and t. Okay? So, to get from here to here, all I have done is to expand w of y. You see gamma is w of y minus w of 0. So that gives you this term here, the first term. And with some little effort, you can convince yourself that this term provides exactly this. Yes, I mean, this term is obvious. What is not completely obvious is how to arrange these two terms, but this is the result. Okay. So now let me. So it's not a difficult calculation. It's just that it takes a few lines. Okay. Now I want to make a comment about the various terms. As I already mentioned, we have done approximations which are based on the expanding. We were assuming that some terms are small compared to others. And what I want to show you here is that the terms which have been written on the board actually are all of the same order of magnitude. And I want to comment on that. Let me let me scale the time. So T, I'm going to scale by the temperature in order to form a dimensionless quantity, and that I'm going to call tau. And let me divide left and right by T. So I will get d by d tau times d by d tau times d of r, y, and let's see, it's an absolute notation, function of tau. So now the next term, so the term L0 is of order 1 over m times gradient y. Now, gradient r indicates how much things vary when the quark move a little bit. I mean, this is r refers to the density. This is the diagonal part of the density matrix. So gradient r, I'm going to assume that gradient r is of the order of the wavelengths. I'm going to look at variation over this type of distance scale, and gradient of y will be also of the order of the thermal wavelengths. The reason being exactly the same as I was mentioning before. You need, there are specific interference effects between the components of the density matrix, and these interferences die out if the distance between the 2 points r and r prime exceeds the thermal wavelengths. I mean, when this distance is bigger than the thermal wavelengths, you can consider the particle as a classical object. So basically, these are the order of magnitude. And remember, the thermal wavelengths is of order 1 over mt. Of course, when I say, I'm talking about the inverse gradient, right? So I have, this is L0 over T, so this is mt. So this is of order 1. So in this new variable here, the first term, the kinetic energy, is of order 1. I've scaled things, I arranged things in such a way that this is, it is so. And then the other terms. The other terms, well, the other terms have the following structure. For example, gamma of y. Remember yesterday, I mean, and even today, we argued that the gamma vanishes when y goes to 0. And yesterday we argued that this... obviously. Thank you. Thank you. Yes. Yes, now that makes sense, yes. So gamma goes like the square of at very small y. And remember that what controls the variation is the Debye mass. So it's certainly at small y proportional to md times y. It's also proportional to alpha times the temperature, alpha being the strong coupling constant, or I mean, it's g squared over 4 pi. So this can be written, again, for y of the order of 1 over square root of mt. This is alpha t times m Debye squared divided by mt. And if I calculate gamma of y over t, which is what I have to do to compare the terms, alpha m Debye squared divided by mt. And this is alpha times m Debye over m times m Debye over t. Now, this is certainly much smaller than 1. M Debye over t is a number of order 1. Strict weak coupling is small. Alpha is supposed to be small, and m Debye is supposed to be much smaller than the mass of the heavy quark. So you see, the second term here, which comes from the expansion of gamma, is small compared to the kinetic energy. Now the question is what happened with the last term. But you see the last term is essentially the same because there is a factor 1 over mt, there is a factor y which is proportional to lambda. One was square root of mt. There should be of the same order of magnitude, which, yes, it is. It is. Because you see, I mean, I can argue the following way. Here I have y squared. Y squared I have argued is 1 over mt. And here I have the factor 1 over mt, and y times gradient of y is over the 1, whatever scale you choose for y. So these two terms, so what I'm saying here is that in this equation, I have a kinetic energy which is over the 1, and I have two terms which are much smaller than the kinetic energy, but which are of the same order of magnitude. So you see, in the expansion I was doing before, where I retain, and it was okay for the correlator, only the term gamma, and ignore the term which involves the velocity of the particle, I was dropping a term which turned out to be of the same order of magnitude, at least in the semi-classical regime, than the term I had kept. Okay? But now I have a consistent semi-classical approximation for D and the equation, and I can start playing with it. So I will convince you about orders of magnitude. I'm going to use a tool, a common tool for this type of problem, which is to take a Wigner transform which is nothing but the Fourier transform with respect to y. That is to say, I'm going to describe to write the function d not as a function of y, but a function of momentum p, and that function is defined by taking the Fourier transform p dot y of d of r yt. And if I do that, I can transform the operator L, which is sitting in the square bracket here, into the following expression. Because minus p over m dot gradient r plus a half of gradient p dot h of 0 dot gradient p plus 1 over 2 mt times p h of 0 times p. Okay, these are all vectors p. And now perhaps I will simplify a little bit further. I'm going to assume isotropy. It's not a big thing. I mean, it's just to simplify this expression. So if I assume isotropy, I can write this Hessian matrix as the following: 1/3 delta ij, and this I'm going to write as eta times delta ij, and I'm going to set eta, at the moment it's just a notation, 2 gamma times t. Then from here I write the following equation for D, for the density matrix, plus V dot gradient with respect to R times D of R, P, and T is equal to 1/2 eta gradient P squared times D plus gamma gradient P dot with velocity times D, where the velocity here is just P over M. And that's it. So this is what? This is just a Fokker-Planck equation, which describe, if I allow myself to interpret D as a phase space distribution, which is not quite the case in general, but in the semi-classical regime, this takes the interpretation of phase space distribution functions that give, if you wish, the probability to find at location R a particle with momentum p. Then this probability distribution, or phase space distribution, is described by an evolution equation, which is written here, and which is a Fokker-Planck equation. You see that there are two terms in this equation. There is a term which is a diffusion in momentum space. That's a gradient square. That's a diffusion equation in momentum square. There is a drift term here, which I'm going to ignore. It depends on the density. If the density of particle is not homogeneous, there will be a drift here. And then there is a term here, which is a drag term. It would be good to have new chokes. It's hard to write on this board. And the drag term, which will have the effect of slow down the particle along its direction of motion. And you see, I have written this in using conventional notation for Fokker-Planck equation, or the associated Langevin equation, which I will write in a second. But these two quantities are related. And they are related, obviously, because they come from the same basic quantity, which is this Hessian matrix, which is defined here. So I have introduced two names for essentially the same quantity, but these two quantities, one which involves the diffusion and the other involving the drag, are related generally by the so-called fluctuation dissipation theorem, or Einstein relation. It's a guarantee that if you let the system evolve, it will eventually thermalize with the surrounding heat bath. Okay? So everything comes out nicely. At least one starts to recognize things which are being used actually for phenomenology without going through all this derivation. But there are issues which I may or may not comment on the phenomenology, which are, to me, have been missed. Let me just complete the story by writing the equivalent Langevin equation.